Note that this presentation is not meant to replace your reading of Section 5.2 in the textbook. While watching this presentation, it would be very helpful if you follow along in the corresponding portions of Section 5.2 from your text. Lastly, please note that you're responsible for reproducing all parts of this presentation on paper according to our course guidelines for formatting of written work, except for any portions that appear in italics or any slides within the presentation that are specifically identified as not requiring reproduction. So let's begin by talking about a point estimate for a population proportion versus a confidence interval. The sample proportion, p hat, provides a single plausible value that is a point estimate for the population proportion p. However, the sample proportion is not perfect, and it will have some standard error associated with it. Therefore, when stating an estimate for the population proportion, it's better to provide a plausible range of values, known as a confidence interval, instead of just supplying a point estimate. So how do we construct a confidence interval? Well, since p hat is the most plausible value of the population proportion p, it makes sense to build a confidence interval around that point estimate. Therefore, the standard error is what we use to provide a guide for how large we should make the confidence interval. Recall from section 5.1 that the standard error represents the standard deviation of the point estimate. When the central limit theorem conditions are satisfied, the point estimate closely follows a normal distribution. So in a normal distribution, 95% of the data is within 1 96/100ths standard deviations of the mean, which is easily checked using some technology tool like RGuru, and noting that the probability of z being between -1 96/100ths and +1 96/100ths is approximately 95%. Therefore, we can construct a confidence interval that extends 1 96/100ths standard errors from the population proportion, from the sample proportion, to be 95% confident that the interval captures the population proportion. The next slide is going to contain all of this information in a sketch format. You must reproduce the slide as the first page of your notes for this section. Please note that drawing interval sketches is going to be a required part of constructing confidence intervals for this course. Note that the sketch has the p hat axis scaled in units of standard error, up to a max of 3 standard errors above, and down to a minimum of 3 standard errors below the point estimate. So here's the slide showing what a confidence interval would look like. Notice the middle portion between p1 hat and p2 hat, which are the endpoints of the interval, is shaded. And then notice I've scaled the p hat axis in units of standard error. And then down below we have a z-axis, and I have the negative z asterisk and positive z asterisk values corresponding to 95% confidence interval in this case. On the right-hand side, we have the formulas for calculating the endpoints of the interval, including the margin of error formula. And then down below, the bottom box shows the 2 different ways that we can write a confidence interval for this course. Now, because what we just discussed is a little bit on the theoretical side, it would be helpful if we went ahead and looked at an example and see how to actually construct a confidence interval. So I'm going to go ahead and combine example 5.8 from your textbook with the 4-step process for constructing a confidence interval that is shown at the bottom of page 184. You will need to reproduce all work associated with this example, starting with the problem statement below. So here's the problem statement. In section 5.1, we learned about a Pew Research poll where 88 7/10% of a random sample of 1,000 American adults supported expanding the role of solar power. Compute and interpret a 95% confidence interval for the population proportion. So we start our 4-step process with the prepare step. We're going to identify the sample proportion p hat and the sample size n and determine what confidence level we wish to use. So in this case, we were given the information that the sample proportion is 887 thousandths, the sample size is 1,000, and the confidence level is 95%. Moving on to the second step, which is the check step, we're going to verify the 2 conditions to ensure that the sampling distribution of sample proportions is nearly normal. For one proportion confidence intervals, we're going to use the sample proportion in place of the population proportion P to check the success-failure condition. So starting with the independence condition first, since we took a simple random sample of American adults, that means that the observations are independent. We now move on to our second condition to check, which is the success-failure condition. Using the substitution approximation, where we substitute the sample proportion in place of the population proportion P, we find that the number of successes given by the formula n times p hat is equal to 887. The number of failures in this case, given by the formula n times 1 minus p hat, we find that there are 113 people that did not vote in favor of the solar power proposal. So since both values are much greater than 10, the success-failure condition is satisfied. Also, please take note of the fact that when we look for the numbers of successes and failures, we will always round that to the nearest whole number in this course. All right, so as our concluding statement, since both the independence and success-failure conditions are met, we can model the sampling distribution of sample proportions as an approximately normal distribution. Now we move on to our third step, calculate. If the conditions hold, which in this case they both did, we're going to compute the standard error using the sample proportion p hat. We're going to find the z asterisk value, that is the z-score value that corresponds to the confidence level, and then we'll construct our sketch of the interval. So the standard error is given by the formula shown on the screen. Getting out a calculator or using one of the RGuru calculators, which I encourage you to do, and turning the crank, we find that the standard error value is approximately 10 thousandths. The z asterisk value, which would be found also by using RGuru, and I will show how to do that in a later video. In this case, we know already that it is equal to 1 96/100, since that's the z-score corresponding to a 95% confidence level, as we saw earlier. All right, so now we start to form our sketch. Notice that I have drawn two axes, a p-hat axis and a z-axis, with the tick marks up above one another. And in the center of the p-hat axis, I have put our sample proportion value of 887 thousandths. I'm now going to scale the p-hat axis above the 887 thousandths value by adding the standard error value of 10 thousandths, going up 3 standard errors, and then I subtract 10 thousandths to go below the p-hat value of 887 thousandths until I'm 3 standard errors below that value. All right, the next thing we're going to do is we're going to include some vertical lines that go through the plus and minus z asterisk values. Remember, those were negative and positive 1 96/100. We then label those values down below the dashed lines, and then we shade the interval on the p-hat axis. This is the confidence interval that I have just shaded in between the two vertical dashed lines. All right, moving on. The last thing we need to do is we need to calculate the endpoints of our interval, the left and right endpoints, and add those to the sketch. So we begin by noting that the margin of error, which again we can find using a calculator, either an RGuru calculator, or if you happen to have a calculator, you can use that. I would encourage you to use the RGuru calculator since you're only allowed to use those on tests. When we multiply the appropriate values for that formula, we get 196 10,000ths for the margin of error. Then we calculate our endpoints by subtracting the margin of error from the sample proportion value to get p1 hat, and adding the margin of error to the sample proportion to get p2 hat. And I then go ahead and I add those values to the confidence interval sketch. And we see that on the left-hand side, it is 8,674 10,000ths, and on the right-hand side, it is 9,066 10,000ths. And that completes our sketch. All right, the last part of this the last part of what we need to do as we finish our sketch up is we need to write a mathematical expression of the confidence interval. There are two ways you could do that. Method number one is to write the sample proportion value plus and minus the margin of error as you see on the right of that formula. The second way, which is the most common way, this is the way I would encourage you to continue to do to write the interval is using what's known as interval notation, where we just put the parentheses on the left and right and then the two values for the endpoints in the middle. All right, the fourth part of this process is we need to conclude by interpreting the confidence interval in the context of the problem. And so we can now state that we are 95% confident that the actual proportion of American adults who support expanding solar power is between 86 and 7/10% and 90 and 7/10%. Notice that when we rewrite the decimal values that we found, we write them as percentages to the nearest tenth for any conclusion statement in this course. And that concludes this presentation.